All right. Thank you. Thanks, David, for this amazing gift. Sally, for your introductory remarks, wherever you are, and Jim for being such an inspiring leader. Every time I see you talk about this, I'm re-inspired all over again. All right. So my name is Josh Tenenbaum. I'm one of the scientific directors. I've been part of CBMM and the Quest from the beginning, and it's a great pleasure and honor to be bringing you to this session here, which is bringing you the leaders of two of our missions. In addition to myself, Laura Schulz and Rebecca Saxe are leading the Development of Intelligence mission, and Jacob Andreas and Fedorenko are leading the Language mission. And I'm going to do a bit of stage setting, talk for about 10 or 15 minutes or so, just to give you a picture of why we're doing what we're doing, what is the relationship between language and the development of thought, which is on all of our minds these days. And then we're going to have a conversation, a structured conversation, where you're going to see the many kinds of things that this team is thinking about, how we're thinking together, how we've been working together, what our next steps are, and some of the kind of impact on society that Jim talked about. But let's start off with our North Stars. Where do we hope to get to? Well, imagine if we could build a machine that grows into intelligence the way a person does, that starts like a baby and learns like a child. This has been the oldest dream, the original vision, going back to Alan Turing, for how to build an AI system. And for good reason. Because if you think about it, a human child is the only learning system in the known universe that reliably, robustly, reproducibly grows into full human intelligence, starting from less. So if we could understand that, it would be a roadmap, a guide, maybe its own kind of scaling route for building AI. But of course, more fundamentally, it would be a way to understand ourselves, where our own minds come from. If we had something like this, think about all the other kinds of technology this could enable. Imagine if we had robots that you could trust to help you out around the house and learn new tasks in new environments as quickly and as easily as another person does. Or imagine if we had systems like ChatGPT, which you could ask any question and expect a reasonable answer. But inside, they're not just black boxes trained on all of humanity's data. Instead, they're our best current models of how human minds think and communicate. These may seem like science fiction, but increasingly, they are starting to seem kind of attainable. And the research that's going on in the Quest, and all the ways in which we're also working with outside groups, are quite seriously, I think, taking steps towards delivering what we hope will be the positive impact versions of these ideas. But AI today, let's look at AI today a little bit, right? I mean, I shouldn't say but AI today, and AI today, right? AI today is remarkable. It's gone from an academic field to a thing in everybody's lives and affecting every part of our society. And there have been remarkable systems, real, in some sense, prototypes of these things. Robots that actually are there in the world making life or death decisions, otherwise known as self-driving cars, like Tesla or Waymo. And they save lives and they take lives. And so far, I think they save more lives than they take lives, but it's unclear. Or language-based AI, conversational system, ChatGPT, or Google's Gemini, which is now, you can't do a Google search without having an AI chatbot giving you answers whether you like them or not. Right? So we're going to start off in this session reflecting on what are some of the similarities and differences between today's AI that the biggest, most valuable companies and the world's richest people have been leading and betting on. What are the similarities and differences between these systems and what we've come to understand about our own minds and brains? And all the ways in which both the similarities and differences are opportunities for these bidirectional interchanges between the science and engineering of AI, as Jim talked about. We'll talk some about what are the activities we've been doing to address these opportunities, where are we going next over the next 2 years and beyond, and again, what are some of the impact? So I'll give you my perspective first. Again, these are amazing systems. It's truly remarkable that we actually, have these robots in the world, okay? And yet, there's something sometimes head-scratchingly weird about where the successes and failures, how they pattern together. So for example, Waymo it drives truly autonomously, but only in some parts of a couple of cities. Tesla, you can drive on any road in the United States, but you might have to intervene, or you do have to intervene on average every 13 miles. So there's something very different here, and we're far from having a complete solution, even to the limited version of robots that just stay on the streets, okay? Despite hundreds of millions of dollars of investment. A lot of progress is being made, but it's hard to say how long it's going to take to get there. Or like in conversational AI systems, so Gemini, this is Google's version of ChatGPT. This is the latest, most advanced model. Okay, you can ask it. I can show it the picture I just showed you and say, tell me what's in this image, and it will do a great job of describing it. If you can't read it, it says the image shows the interior of a Tesla vehicle, specifically the driver's seat area with the dashboard, all this stuff. The accompanying text is a headline and subheading from an Ars Technica article discussing the limitations of Tesla's full self-driving system. Amazing. Okay. And it didn't just get that, because that's actually, didn't just get that from the web. That's a mashup I made. That's not an actual web page. But it did a good job of seeing it. Looks like an actual web page. But suppose we give it something that's a little bit, as we say, out of the training distribution. A little bit less of a typical image. This is one from my colleague Vikash Mansinga, who you've heard already a little about. You'll hear a lot more from him later today. This is an image that's designed to test a probabilistic inference systems of the sort you'll see here. Okay. You can all read it. What does it say?
Uncertainty.
How confident are you? How certain are you? Any uncertainty? No, you know what it is. Okay. But this very same system says the image shows the CAPTCHA 52GCSIH5ZB2. Well, it recognizes it as some kind of a CAPTCHA. That's reasonable. But that's not the right answer. And when asked how confident, it says, well, I'm around 70 to 80% confident. The G, L, and 2 I can see, although they're the ones I'm the least certain about, but the rest I can see pretty relatively clear. What's going on with that? Or maybe it's just a little too hard, so we can make it a little bit easier. Now we just showed it certainty. What does this show? The image appears to be a very low resolution and noisy rendition of the word CAPTCHA. It simulates the visual challenge aspect of a CAPTCHA test. Huh. How confident are you? Again, I'm 75 to 80%. While the image is very noisy, the general shapes of the letters are discernible. The P, T, and the second C are the clearest. Okay. So what's going on? Well, again, to build on some of the themes you heard from Jim, what's driving these systems? Again, amazing technology that's designed to simulate what in some sense, the input-output relationships of a mind, to take the inputs that we might have with our brains in the world and produce the outputs by training what is effectively, and in some important way, just a big black box full of very simple little elements that when you scale them up and make them big enough and train all the parameters on all the data you can measure or simulate from the world, the internals of this black box system, in some ways, really quite surprisingly, have these emergent properties where something really genuinely intelligent seems to emerge. And yet it's unpredictable and clearly very different than the way our minds work. Okay, and we'll again dig into that in different ways. What you sometimes heard of the scaling laws, this is where some of the interesting theory of AI comes in, whether it's these scaling laws of learning or the scaling laws of inference, which we'll be talking about later. Okay, inference is more like online thinking. Scaling laws of learning is what happens when you add in more and more data and offline compute, the millions and increasingly close to billions of dollars that are used to train these systems. Some performance reliably increases. Every 10x compute is another increment of performance. But it's performance on the things that you can easily measure if you're a big tech company, which is how well you predict the next letter or the next thumbs up or maybe the next dollar, but not the next increment of intelligence. Nobody yet knows what are the real scaling laws of intelligence. So these are very unpredictable bets. In contrast, something different is going on inside our minds. Our minds are built, as Jim said, to model the world. That is the physical world and also the social world. So I'm going to turn it over now to my colleagues, starting with the developmental researchers, to say something about what is different about the way our minds are built from the beginning. So go ahead, Laura. Yeah.
Terrific. First of all, thank you all for being here, and it's a real pleasure to be part of this incredibly inspiring and ambitious event. I think we all know that today's industry AI is actually getting closer and closer to human-like performance. And we also, I think, all know that today's industry AI is deeply and really unlike human intelligence with respect to learning. And the simplest respect in which we all know that is true is the amount of data that it takes. So children learn from tiny amounts of data, sometimes just 1 or 2 examples. We can't learn from big data. Industry AI can, but it has to. It doesn't have any alternative choice. And to give you a comparison, I think the amount of data used to train GPT-4 relative to the input to a human child is approximately the difference between the population in this room and the population of Tokyo. So that's a very, very different scale of measure. That's the thing I think we all know, but I think there are at least 3 other respects in which children's learning is really different, human learning, that is to say, from AI learning. An artificial neural network will learn from whatever you give it. It will learn from any data set at all. For better or for worse, human children do not do that. Babies are selective learners from the start. They choose what to look at. They choose how long to look at it. They choose when to look it away. And as soon as they can act on the world, they pursue their own goals, their own problems. Nobody in the history of the universe has ever told a toddler to try to put clothespins on a cat or Play-Doh under the couch to catch a velociraptor. Children do things like that every day. I did not, I promise you, tell my daughter that what she should do in the library was climb the shelves of the children's room. She decided to do that. I promise I knew they were bolted in before I snapped the photo. But children choose what they want to learn, and they explore in that way. And they don't just learn from data. They learn from other human beings. They ask questions dozens of times a day. And the questions they ask are ad hoc, idiosyncratic, often maybe the first time that question has ever been asked in the universe. They invent things to ask about. And the information they get and the information they share, at 10 months, they start pointing and showing us what they want to know. They take your hand. They take you where they want to go. The information they get, the information they share, and we share with them, is neither arbitrary, nor is it a representative sample of all observations. It is tailored specifically to their abilities, their knowledge, their interest, and their goals. And I think something we can sometimes forget as cognitive scientists and as AI engineers is, of course, children don't just learn and teach from other people. They want to connect with other people. They care about them, and they care for them. And this is a really important and central part of what it means to be human, what our motivational system is like. But I think maybe the least recognized and maybe most fundamental way that human learning differs from today's AI is today's AI is profoundly not developmental. In fact, in some sense, it is profoundly not about learning. Because think how odd it is that we have systems that can do better than human biologists at protein folding, and they don't know what a protein is, and they don't know what a cell is, and they don't know what a body is. Today's AI can start very, very dumb and become very, very smart, and that's nothing like human learning. Humans are intelligent from the start. We start out intelligent at simple things, and then we become intelligent at more and more complex things. Our learning is cumulative. And I think the grand challenge for the next generation AI is to understand and engineer an intelligence like this, an intelligence that is always intelligent and where it's cannot and does not have radical gaps and discontinuities in its learning because knowledge grows systematically.
So fun. Thanks. So I'll just continue on that theme and talk a little bit about the work that we've done, actually on exactly the same ideas that Laura just mentioned, but now with babies. So Laura's talking about the selection of input from a 10-month-old. This is a 4-month-old. Actually, each point is the point of gaze of a 4-month-old preverbal baby who could look at anything. But you see they choose what they're looking at really systematically. All the babies are looking at the faces and the hands. So these are babies who, before they can move any other part of their body, are choosing how to learn from the world by choosing what to look at. And one of the privileges of working at MIT is that we can study that initial architecture, the architecture that drives what babies choose to look at and learn from before they can move. And we can do that using neuroimaging. So Josh was talking about the model of the world inside the mind. We can look at it literally, the model of the world inside the baby's brains. And one of the places that we started this research was looking for how people see faces and each other, this kind of core motivational system. We've known based on incredibly important discoveries at MIT. I don't know if you all know that Nancy Chemischer won the Kavli Prize, the highest prize in neuroscience, for the discovery of these face regions in human adults. And we've been continuing that work, trying to ask, where do those come from, right? Do we have to learn them slowly with hundreds of thousands of hours of experience like an AI system? And of course we don't. So we've been developing systems for brain imaging of human babies starting from 2 months. And what we've discovered over the last couple of years is that the system for seeing faces that adults have is the whole architecture is there by 2 months old, the earliest we can measure it. A really powerful example of the thing Laura was telling you, that baby brains start with all the tools to learn from the world that they're going to experience.
So let's now turn over to more the language side. Yeah, starting with Ev.
Sure. Hi, guys. How do I click to advance? Sorry, the right button?
Yeah.
Okay, so I spent a lot of time in the last 20 years thinking about human cognition and how language might figure into this. So with these kinds of early developing capacities that Laura and Rebecca mentioned, by the time we are an adult, we can do all sorts of things in the world. We learn concepts from very concrete ones, like what an apple is, to very abstract ones, what is justice, right? We learn to reason about concepts and the relationships between them. We learn to understand the physical world, how gravity works, how objects interact, but also the social world, how agents relate to each other, how to cooperate to achieve goals. We also learn to reason in fundamentally abstract ways that are not really tied to any particular knowledge base. We can solve novel problems on stimuli that you've never experienced before. And this kind of ability to reason abstractly is tied to these very fundamental capacities like attention, working memory, understanding what a goal is and how to work toward a goal. We create and appreciate art. We can estimate numerosities. We invent strategy games like chess. The question that has been puzzling me for many years is, how does language fit into this? To what extent is our cognitive sophistication enabled or unlocked by language? And of course, a lot of these abilities in some form we share with other animals. I'm marking those with green check marks, right? In some form they exist in other species. But there's also some which I'm marking in red that seem to be specific to humans. And in some ways, some of these human-specific abilities are, in some sense, trivially enabled by language through the accumulation of knowledge that language enables us to pass from one generation to the next. If we had to reinvent things from scratch in each generation, we couldn't figure out calculus. We couldn't build and program machines. We couldn't create narratives that capture the history of the humankind. But when I started working on these questions, I was interested in a bigger claim, which is the claim that we use linguistic representations, words and structures, to actually engage in thinking, which is a claim that many people have made over the years. So these are just example quotes from Chomsky, where he wrote things like, "The systems of thought use linguistic expressions for reasoning, interpretation, organizing action, and other mental acts." And he further speculated that a substantial part of what we call thinking is simply linguistic manipulation. So if there is a severe deficit of language, there will be a severe deficit of thought. And he kind of states these things as if they are truths, facts about the world. But of course, without data, they're just hypotheses. And I wanted to test them empirically. And so over the last bunch of years, with many different colleagues, we've used two approaches to try to ask whether these ideas are actually on the right track. And the way we can ask about the relationship between language and other things is in two ways. One, we can find your language areas. If you come into the lab and we put you in the scanner, in about 5 minutes, we can find the parts of your brain that do language, and we know that reliably. And then we can ask, how are these areas working when I'm asking you to solve a math problem, or when I'm asking you to read a piece of computer code if you're a programmer, or to solve a logic puzzle like Sudoku? Right? And we find time and again across many, many different tasks that your language regions are actually silent when you're engaging in many, many different kinds of thinking. Other parts of the brain are working hard, but the language representations don't seem to be engaged. And in a complementary approach, we can look at patients who have problems with language, aphasia, right? So some of you may have relatives who have this condition. Typically, as a result of a stroke, you may lose some parts, or sometimes the entire language system, and lose your ability to produce and understand language. And again, we can ask, okay, these patients have trouble communicating linguistically, but can they still think? Like if they could play chess before, can they still engage in chess? If they were writing music, could they write music? If they were a mathematician, could they still do math? And it turns out that a lot of these abilities appear to be preserved. So it doesn't seem like even losing language can still allow you to engage in these very sophisticated mental acts. So the answers to these questions seem to be that no, the language system is not working when we're doing these kinds of thinking tasks. We don't need linguistic representations per se. But of course, language is very deeply embedded in everything we do in the world. Like it's very hard to imagine our everyday life without language. And I think next, Jacob will talk about the implications of this dissociation between language and thinking for how we build better machines.
Let me just do one sort of, again, stage setting thing. So you've heard now from three of my colleagues in brain and cognitive science, like laying out from their different areas of expertise, like what we tend to what we've come to understand about human minds and the relationship between language, like the ways we're built for intelligence from the start, the ways language adds onto that in clearly amazing ways. It's clearly a superpower of humans, right, as Ev was saying. I mean, it trivially enables culture, but it enables culture. And it's the most obvious difference of us from other animals. And yet we see something that might look sort of different from the route that we're seeing with today's amazing language models following a different path. So Jacob is a member of CSAIL. He's one of the world's experts in natural language processing and language models of all kinds. And so let's turn it over to Jacob to say, like, tell us about some of the differences there. Yeah, or similarities and differences.
Thanks. Yeah, and I guess to start by sort of setting the stage here, I want to say something that basically everybody on this stage has already said in computational terms, that when we think about what it is that's going on in human learning, all the things that Laura was talking about, such that when you're born, you're able to immediately start sort of engaging in complicated exploration and play and learning from very small amounts of data. Obviously, these things don't come from nowhere. They are the result of a very long evolutionary process that, where evolution, even if no individual learner has seen, data comparable to a learner's data, like the room scales with Tokyo. But I think an important difference there, an important thing to keep in mind is that almost none of that data, to a first approximation, none of that data is linguistic, right? Whatever it is that evolution has seen, whatever it is that evolution has done that puts you in that magical state that you're in as an infant when you start learning, really has very little to do with language. Specifically, it has everything to do with, the kind of more general families of reasoning and learning problems that, the sort of entire history of life has experienced. And this is totally different, again, from the ways in which we're training language models right now, and really sort of AI systems of all kind right now, where the very first thing that we do is we download all of the text on the internet, the sort of end result of that process that has generated humans in their current state, and we train a really good predictive model on that text, on that language data, on all of these sort of sort of accumulated knowledge, accumulated linguistic data that are exactly the things that human language learners don't need that much of. And so when we start to think about what it would look like to build more human-like intelligence, and what it would look like, especially to build machines that can kind of learn on the same timescales from the same kinds of data as humans do, I think this is really the sort of big difference that we have to grapple with, and to think about what are the kinds of things that we could build in, or at least what are the kinds of other learning problems and the kinds of other data we could present our learning algorithms with, such that they would really be able to make do with very little language data and generalize from very little language data, but also all of the other kinds of experience that human children have access to. Without having to do these large-scale things. And I think this would, obviously have sort of engineering consequences in terms of the amount of data that we would then need to train models and the amount of work that we would need to do to fine-tune them, but also really, I think, fundamentally change the kinds of generalizations that we would expect to see from these systems, the kinds of robustness we would expect to see from these systems. And, I think if we're going to answer this question, then we also need to be able to start to ask even more basic questions about what kinds of non non-linguistic capabilities, what kinds of general purpose reasoning abilities, what kinds of, sorts of algorithmic thinking and algorithmic generalization might we expect to see in systems that look like modern language models, so that we can start to think about what those other data sources and what those other sort of architectures of the future might look like. And so one of the things that we have started to think about a lot here is exactly these kinds of basic questions about, can you, in this function fitting paradigm that Jim and Josh were describing before, even implement anything that looks like algorithmic reasoning? And what can we say about the kinds of algorithmic constraints that exist on the sorts of models that we have right now? And I think what we're seeing so far is that this is actually a fairly complicated picture. On one hand, with exactly the right data and with exactly the right amounts of the right kind of data, you can actually take a thing that looks like a modern transformer language model and get it to implement, sort of inside its head, so to speak, things that look like classical learning algorithms, things that maybe look a little bit more like what it is that we might want a human-like language learner to do with small amounts of data, but incredibly inefficiently and incredibly sensitively to the kinds of data that they're trained on. And maybe bring this more explicitly to the point about world models and the extent to which we should expect things that look like modern language models to actually build representations of the outside world, to plan, to reason, to simulate, to do things like that internally. Another question that you can ask, and something that I think people are talking about quite a lot in the sort of industry AI world, the world of language models and other kinds of large-scale machine learning models, is the extent to which these big neural sequence models contain things that look like world models, or whether you can learn things that we would be, even with our neuroscience hats on, inclined to call world models, just as a result of training on very large amounts of language data. And again, the answer here is messy, but I think mostly that you get only very rudimentary forms of these models and only from very, very large amounts of language data. And I think fundamentally this is because language data is just not the right kind of data from which we should really expect these models to emerge. And so we'll talk a little bit more about, I think, some of the sort of concrete work that we've been doing in the scope of the quest to address some of these limitations and to think about what other learning algorithms, other model architectures, other data sources might look like. But maybe the main point that I want to make now is just that on one hand, I think there is starting to be promising evidence that you can get some kinds of structured representations inside these big neural models if you set them up in the right way. But on the other hand, the ways in which we're setting them up right now really seem not to be the ones that even, either if you want to build sort of like an explicit computational executable model, or if you want to do something more implicit that lives inside one of these neural sequence models, that you're not going to get it just by training on kind of all the language data in the world and nothing else. And there's one more slide, which I guess is going to sort of cue up the next section, which is that, one thing that you might ask then is what other paths we have and what other kinds of models might look like that could do this. And I think one thing that we're actually going to spend quite a lot of time talking about today is that, obviously there's an enormous tradition of work, much of it actually coming from people who are on the stage right now at MIT, at building sort of explicitly computational models of how human intelligence works that bottom out, not in sort of transformers and generic neural architectures, but like real computer programs, symbolic descriptions of the kinds of computation that people are performing. And one thing that I think is really quite exciting about these kinds of models right now is that as these more general purpose neural sequence models get better and better, they actually give us also the ability to build better, more explicit symbolic world models. And I think this is actually a sort of place that we see the field moving as a whole, but towards large-scale neural sequence models that are reasoning about the world, that are simulating the world, not just by doing this kind of implicit neural computation, but by actually building and reasoning about and executing explicit computational models of how the world works. And with that, I think we're into the next section.
We have two different control. Okay, yeah. I'll just do it from my laptop. So I just want to sort of, again, sum up the picture that we've seen and then talk about like this sort of the background of what we're doing, which I think can be summarized with these two sets of bullet points. So just as Jim said, like if you're gonna remember anything from this session, I think this is a set of important points, which I'm trying to summarize in 3 bullet points each. Like, what is the essence of the kind of route to building intelligence that we're seeing driven by today's massive investments from industry? And on the other side, what do we see the way intelligence seems to grow in human minds and brains? And what might be another bet, another scaling path perhaps for tomorrow's AI, right? The Quest and the Quest researchers engineers, our tools, our virtuous integration between science and engineering can address both of these. They can help us better understand the left side and better build the right side, okay? But just to sum up these points, right? In the sense, the industry scaling path, the deep learning, massive data, massive compute, has a notion of learning, in quotes, that is, that's the optimization path Jacob was talking about, which is simple and dumb by design in order to be scalable, right? The kind of learning that goes on in the weights of a neural network isn't supposed to be smart. It's supposed to be just a small little gradient step on some big end-to-end differentiable function, okay? But the idea is you do that enough, and something that you could maybe legitimately call intelligence in some form emerges as the end state, right? It's surprising, remarkable, but also kind of fragile, because intelligence, and the hallmark of intelligence is the ability to solve new problems or generalize. Generalization is another one of these emergent properties. It's not built in, but it depends on similarity to the training data, okay? And as a result, it's unpredictable. And again, like I showed you in the examples we saw. Some kinds of generalization are predictable, but the ones that are really about understanding the world are unpredictable. And then crucially, the relation between language and thought. The reason why we're up here so much focused on language, and the reason why the big transformers, the big machine learning models, the only reason why the entire world is now talking about and using AI in the way that they didn't before, is because language is a superpower. And training on all the world's language data that's ever been produced for Tokyo city-size lifetimes, is something. But again, it's this idea that intelligence has to, or that intelligence emerges, or thinking emerges after language, distilled out in some, or backed out from language. In contrast to the human root, right, where we're built to be intelligent from the smart, it's intelligence in some form. It's not that, of course, adults are in many ways more intelligent than young babies. Maybe not in all ways, but intelligence changes with learning. But intelligence is crucially a thing that's built in from the start that lets you learn so much from so little. That's fundamentally oriented around our brains and minds being built to have certain kinds of models of the physical world and of each other's as agents, even with even faces and the interface through our eyes and our shared attention. And then this idea that thinking is independent from, exists before language, and language grounds on that. So what we're doing, especially in the developmental root of the quest, I'm just now going to tell you a little about my research, is we're building computational models, engineering-style models designed to reverse engineer and follow this alternative scaling path. So that means understanding what's built in and how do you learn the rest. That's this developmental roadmap. And again, to take the kind of things that my colleagues have been talking about here and that we, in our collaborations, build together, it's understanding the representations and algorithms. So not just function approximators and optimization, but symbolic models of the physical and social world, probabilistic models, fundamentally the kind of intelligence that we see not just in humans, but in all brains, as Ev showed. You can think of as a certain kind of rationality, making good guesses and bets about what's going to happen next. What are the effects of your actions? What might happen if you acted in a different way? It's that ability to predict and to even imagine ways the world could be and use those to plan your actions. That's what brains do from the beginning, well before there were humans in the world. Brains were doing this kind of thing. In humans, those build fundamentally on these models, as we've been fleshing out here. We'll see more about this. Models of the physical world, but especially the social world, other agents' goals, and understanding how agents' actions depend on what goes on inside their minds, our models of other minds, their goals and their beliefs. Okay. And especially this focus, as you heard from Laura and Rebecca, on goals, on understanding even the youngest babies have goals in how they look and how they engage, how they learn and how they connect to others, and how that and learning about the goals of others is so crucial to how our intelligence develops. So the developmental roadmap, and again, if you want to take one other thing, it's sort of this part here. It's what is built in terms of this core architecture, and then if you want, what we best understand in very high-level terms about the stages of human cognitive development, you can take these three. There's basically before language, and then after language. What kind of learning goes on within the core architecture for the first, say, year and a half of life. Then the major focus of learning over, say, 1.5 to age 3 is learning language. And then once you have language, how do you use that to learn everything else, all the knowledge that accumulated culturally, right? And that you get socially from others. And in order to engineer this, to build models and test them, this can't rest just on the industry computing stack, just bigger and bigger transformers. You'll hear more about this in the scaling inference mission in the afternoon. But we're building, and this is Vikash Mansinga's group and probabilistic computing group at MIT, is building a new computing stack. You'll hear more about probabilistic programs, but new kinds of programming languages that integrate function approximators like neural networks, but also symbolic knowledge representation, symbolic languages, programming languages for expressing all the knowledge of how the world works and what you can do, and probabilistic inference on top of those, inside and on top of those, to make good guesses and good bets, not just about where a ball might bounce, but what somebody's thinking, what we might want to do together. Okay. So that's what we're doing up here. Now, I'm going to turn it back to, again, my developmental colleagues in a second, but I'll just say what we've been doing over the first 2 years of this phase of the quest is trying to use this toolkit to capture, for example, some of the things you saw about it. And you saw this in Jim's talk here, where like the most basic ways that even from infants who are 1 year old or less can understand what other agents are doing, even from kind of weird stimuli. Like so, experiments with 10-month-old, 12-month-old babies show them things like this. You see a blue and a red ball moving around, but you don't just see them as balls rolling on a table. You see one thing is chasing another, and the other one is trying to get away. Or here, you see a red ball that appears to jump over a wall to get to a blue triangle. And in experiments from our former Quest colleague, now a postdoc in Rebecca's lab, also worked with Laura and me, Sherry Liu. She's now a faculty at Johns Hopkins, but continues to work with us as part of the multi-university efforts of the Quest. Study, for example, how infants understand how much an agent, like the red one, wants to be with someone based on how much work they're willing to do to get to them. If even 10-month-old babies understand that if you're willing to jump over a higher wall, there's a lot of songs written about this, you must really want to be with the blue one. Okay. So whether it's that kind of thing that's even present in infants or in classic work with 1.5-year-olds, these are from the studies of Wernicke and Tomasello, ask what lets that 1.5-year-old see an adult doing a weird action that they've never seen before, and just the first time, get a sense of what they're doing and even how to help them, right? What is the intelligence that is, there so early? We're not even talking this room size. We're talking like, yeah, okay. So the kind of models that we've been developing to do this involve, you're sort of seeing a sketch of it here. This is not a model of your brain. It's a model of how your brain models other brains, as Rebecca has long said. That's a good way to think of a theory of mind. A probabilistic causal model that lets you observe actions as the effects of some agent planning. You don't see somebody's beliefs or goals, but you have a model of how they take their goals and beliefs to plan actions that they might reasonably think are efficient, that in some form, mathematically, can lead to achieving high reward or rewarding states, subtracting the cost. So this is what our again, former Quest student, Julian Haar-Edinger, who's now an assistant professor at Yale, hopefully not for long, assistant professor, that is. What he called the naive utility calculus. But this idea that, thinking about maximizing expected utility is something that in some form, even 10-month-olds babies do to try to analyze what goes on in these studies. And by building computational models, indeed simple kinds of probabilistic programs of these sorts of things, of these sorts of abilities that you can see in young infants, this is work that was done in Vikash Mansinga's group with Shen, Tanshi Shen, who's another one of our great, fantastic advanced PhD students. We recently joined a competition, actually, that DARPA, the Defense Advanced Research Projects Agency, ran in trying to build machines with this infant stage of common sense. And in the theory of mind part, we just killed it. So the Bayesian theory of mind, you can see we got like 98% on all the tasks that were set up, these simple kinds of infant benchmarks. But we're not proud of that. We're proud that our systems, which built in the kind of thing that we see built into young babies, do, in some sense, very well on a couple of AI-style benchmarks inspired by developmental psychology. But these don't solve the whole problem. We still don't have robots that can help you out around the house and learn new tasks. And fundamentally, again, going back to what Jim said, we need a much better, bigger, faster, more virtuous cycle of experimenting and benchmarks to drive our algorithms. These very simple first steps need to go much more and faster. So let me turn it back to our developmental psychologists who are working on this. Laura.
So I think, without doubt, the fundamental bottleneck in getting data about human development has been recruiting participants. So up until a few years ago, every single data point to a first approximation that we had about any human child involved calling a parent, scheduling them when they were free next Thursday at 10, and if the child wasn't sick and the parent remembered, they got in a car, strapped the child into a car seat, found a parking space somewhere, pulled the child out of the car seat, and if the child wasn't asleep or fussy and was willing to come into the lab, then you got a data point. And so every single data point was incredibly hard won, and research was slow. And if you wanted to go back to that same child again and test them repeatedly, that was essentially heroic research. Thanks to a brilliant graduate student in my lab, Kim Scott, in 2015, we started building a platform for online automated developmental testing. In 2015, we didn't know what was coming, and one of the things we were worried about was whether we could get other researchers to buy into this and to sign up, because of course, if you want to drive parents to a site on the internet, you need content, and you need to refresh that content. It needs to be new all the time. And we were planning to launch this in September 2020, and then the world shut down in March. And we were able to open this site a few months earlier. And quite amazingly, I have my paper here so I get the facts right. Today, we have 262 labs up on Children Helping Science from 176 different institutions around the globe. There are over 1,300 scientists active on the site right now from 14 different countries. Since the site launched, 13,000 children have participated, unique children, in studies, and almost 15,000 are on the site right now, ranging from newborns and adolescents. And up until now, the site has been, you look for this in your search engine. You can just Google, developmental studies in children and find this and register online. And despite the ongoing digital divide, one of the things I think is quite important is that this site is recruiting a population that is closer to US Census data than almost any data set ever collected in developmental labs. See above on how we used to have to recruit parents to come into universities. Right now, 18% of our population on Children Helping Science has only a high school degree. So this is a really unique population, and as of this fall, we are about to, and thanks to the heroic work of, which is also heroic, of Melissa Klein-Struhl, who I think is somewhere here, and who is the current executive director of Children Helping Science. We're about to launch this on phones and tablets as well. So I think we can really expand the reach. Why does this matter? Well, I think it's not overstating the case to say this has been a game changer in the field. We can now get data overnight. These are, by the way, all studies that are up there right now, the second running currently. We can get data overnight now on children. You can do longitudinal studies now easily, which means we can test the effective interventions. We can do pre and post testing in a way that is no longer horribly time-consuming and expensive. And really critically, we can get the kind of data you need for AI benchmarks and the kind of data you need, the big data you might need to test graded effects in order to test the predictions of these computational models. So it's a new platform. I think we're just starting to tap into its potential, but I think a decade from now, especially together with the tools I think Rebecca's going to talk more about for automated coding, the picture of what we know and can learn about human learning and development is going to change massively.
Thanks. Yeah, so I'll just give one quick example of something we were able to do as a result of this platform and the teamwork of the Quest. So like Laura said, for developmental research, it used to take us approximately 2 hours of time for each individual data point from a single infant. In the most recent projects, supported by the Quest over the last couple of years, we were able to replace each of these with a automated process. So Lookit and Children Helping Science to recruit the families. Instead of having an experimenter have to be there for the appointment and kind of code the experiment as it was going live, we implemented automated parent training so parents can run the experiments themselves from home at any time of their choice. And then thanks to amazing advances in models of perception, the kinds of models actually that Jim was talking about, we can replace an MIT undergraduate coding every frame for where the baby's looking with an automatic model that codes the baby's gaze automatically by using computer vision. This means that it takes the experimenter about 5 minutes to check the data from every infant instead of 2 hours. And this lets us scale up research in all kinds of ways. I'll just give one little example of where we got started. I told you infants choose what to look at. And this is an example data set in a very simple phenomenon in babies, which is in the blue bars on the left under the babies. What you can see is how long a baby looks at a little animated animal, depending on how many times the baby's seen it before. And the red line is for a new animal. This is an incredibly classic phenomenon about baby looking, that they get less interested in something they already know, right? So you can see if they've seen it more times before, they will look less and less. That's the blue line going down. What we were able to do is take the exact images that the babies had seen, all these little animated animals and vegetables, and run them through Jim's model, his CNN model of vision, to tell us how similar each object is to each other object. We use that with a probabilistic program, like the ones that Vikash makes, to model rational exploration. How much would you look at the next object if you were trying to rationally explore the world and make a rational choice between how much you expect to learn from this next image versus anything else you could be doing with your eyes? What I'm showing here is the predictions of that model without fitting. This model just predicts that exactly what we saw in the babies, that you will look less and less at the familiar objects. You will continue to sustain attention on novel objects. And not shown here is we could then generalize this to stimuli that this model had never seen at all. Like, what if instead of 1 cow, now there's 2 cows, right? And the model can likewise make predictions completely out of sample. So this notion of being able to generalize way beyond, into the corner cases, way beyond the examples in the data. And the other thing is that this was possible at the scale of 144 babies in this one little experiment because of Lookit, right? If we had been trying to get 144 babies the way I did this kind of research when I was trained, that would take 4 people's PhDs to get this one experiment done. And instead, this is one piece of one PhD now. And that's at the beta version. That's just as we're getting started.
So yeah, so now let's we'll keep going on this theme of things we've been doing, especially some of our most exciting integrative Quest projects in the language mission that connect both to measurement, modeling, as well as development. So yeah, go ahead, Jacob, and that, yeah.
Yeah, thanks. So, and coming back actually to some of the things that Jim was saying in the beginning of this, a big part of making scientific progress is just being able to sort of measure progress in the first place. And when we start to talk about building computational models of these more sort of general cognitive phenomena, and I guess especially especially models of the outside world and measuring AI systems and natural systems' ability to build models of the outside world. A big challenge here, especially in the, I think, machine learning world, has been that we just really haven't had good data and good evaluation metrics for these things in the first place. Almost all of the kinds of evaluation benchmarks that people used for evaluating modern AI systems are collected much in the same way that the training data is. You just download whatever you can from the internet. You don't think too closely about the sort of distribution over examples and problem instances that you're asking people to solve. And so one of the big sort of Quest-wide projects that we've been involved in that was led by former Quest postdoc Anna Ivanova, who's now a professor at Georgia Tech, was just to build really detailed, really comprehensive benchmark of sort of general world modeling abilities, really grounded in what we know about the cognitive science of these questions, and so have coverage of a bunch of different domains of reasoning, in the sort of social domains, quantitative domains, physical domains, and one of the things that and so we have built this, we've released this, it's in the process of actually being integrated into the Stanford Helm thing, which is like the big major benchmarking system that all the big tech companies use for evaluating their models. And the surprising thing here, I was sort of expecting that with a lot of these stimuli, we would plug them into state-of-the-art models, and they would be simple enough that the very best frontier, sort of OpenAI, Google kinds of things would already do quite well at this benchmark, and it would really just be useful as a tool for understanding what's going on inside these models when they're solving these problems. And in fact, that was not the case. Is that what we see really across the board is that even with state-of-the-art models right now, systems out there are just very bad at a lot of what you think of as very basic social reasoning, very basic physical reasoning, if you evaluate it in a sort of sufficiently dense, sufficiently rigorous, sufficiently quantitative way. So this has been one of the exciting things, is that now we actually have some measure of progress that we can use as we start to build the sort of next generation of models to figure out how we're doing. And so what does that look like? What does that next generation of models look like? To come back to one of the things that I was saying at the beginning about the differences between the way we train modern AI systems, which are sort of language first and then maybe a little bit of everything else, and the way we think about human development, what would it actually look like to invert this equation and to sort of build training procedures and training paradigms that can make use of rich, grounded, embodied supervision of the kind that human learners get, like really right from the very beginning of training? And so this was an effort that Changshu Zhuang, who is another joint Quest postdoc in Evan My Labs, spent a bunch of time working at, and surprisingly found both that the sort of modern recipe of do a bunch of pre-training and then try to bolt the vision stuff on at the end really doesn't work quite well if what you're trying to measure is even sort of knowledge of language as it relates to the world and being able to generate and reason about language that's talking about sort of physical embodied things. But what he was then able to do was to sort of come up with new model architectures, new ways of training these models that for the first time ever actually allowed you to get a language model, even a system that was just better at generating language by virtue of training on a bunch of vision data and not just on more language data.
Can I just say one thing? As one of the Quest leaders and fan of this work, but not participant, I think, and this goes, what Jim said, or some of his worries are also some of my worries, right? It's like part of, in the Quest, like one of the things that keeps us up at night as research leaders is how do we make a new kind of science where teams can do things that people couldn't do before. So these two projects you just saw, the first one that Anya Ivanova led, that was a massive team by academic standards. There were almost 20 researchers, mostly grad students and some postdocs, but 4 or 5 PIs, and it was our first Quest seed funds that made that happen. This was a small team, just these two plus Changshu, I think. But again, it was part of our first Quest seed fund for the language mission, and they did this great thing that won a best paper award. I'm allowed to brag about it because it wasn't my work. This is one of the top conferences in computational linguistics. Only 2 papers won best papers. This was one of them for this last year. And not only was that, but the citation for the paper said it was especially found fundamental and innovative, and especially the cognitive perspective was especially innovative on these basic things. So it's in a small way, but I think it shows that, again, kudos to you guys, and it shows that the bets we've been making, our first steps, I think they really can pay off and move the needle in the community.
Yep. And I think in general, trying to leverage these models to understand development is incredibly exciting, because one really hard thing about studying development is we can't easily manipulate things for good ethical reasons, right? We can't mess with kids' inputs and see what happens, right? So typically a lot of different kinds of things come together during these first few years, and many things co-develop at the same time. But using these models, we can try to isolate different pieces and try to understand how they may affect language learning, and then subsequently learning about the world through language. So in addition to Changshu's work that Jacob just talked about, we are also currently starting to build models that are built on audio data. So Greta Tuchkuta here is leading this effort, because kids don't learn from pre-tokenized text, right? Text split up into little pieces. That's not how they learn. They learn from audio data, from continuous speech streams. And back in the 90s, we as cognitive scientists learned that infants are able to do this because they have very powerful statistical learning mechanisms. So they can learn to detect structure in the patterns of this continuous speech, to detect chunks, which can correspond to words and sometimes to phrases. And for those of you who have raised kids, you may remember how kids sometimes will kind of underparse things. They may think that a whole chunk is just kind of one word, like look at you. They may think it's one thing. And this kind of over-parsing and not chopping language into the smallest possible pieces has been argued to be really important to the kind of efficient learning that human infants do. And so trying to train transformer-like architectures from raw audio may tell us whether this is indeed going to lead to something like more efficient language learning. In addition to evaluating these models on language tasks, like what Cheng-Chu was doing, we can also do the kind of things that Jim was talking about to relate these representations from these developmentally plausible models to human brain data. Okay, so when we first started looking at whether language models can capture human responses to languages in collaboration with Josh back in 2001, we published a paper
2021.
2021, thank you. Okay, I'm recovering from a cold, I'm excused. So we found that a whole bunch of language models like GPT-2, BERT, the kinds of models that you first heard about when they got good, they could capture human responses to language. But a lot of people said, well, what do we make of this? These models are so different. They're trained on so much data. Does it really tell us anything that they arrive at similar representations? And so Eqbal Hosseini, who is here somewhere, did a very nice study manipulating the amount of data that a model is trained at and saw how does it affect the ability of that model to align to a brain representation, right? And he found that actually you don't need that much data. By about 10 million tokens, which is really tiny by current standards, you already arrive at very good alignment with humans.
It's like a 2 or 3 year old maybe.
It's yeah, exactly. A few-year-old kid gets about that. Exactly. Yeah. And now and so Eqbal was just taking text-based models and varying amount of data. But now that we have these more developmentally plausible models, like models that learn both from linguistic inputs and vision, or models that learn from raw audio inputs, we can try to see how those developmental models are able to capture neural responses to language. And not just in adults either. All that we've done so far was trying to take an adult mature language system and try to use these models as models of language processing in adults. But some work that Haley Olson is starting to do, a postdoc between Rebecca and me, is trying to track changes in representations in kids across development. So you can imagine taking a model and training it in some constrained way, and we can, of course, make the model do, we can exactly control what kind of input we get, how we present the training data, and so on, and then see which of these models recapitulate the changes that happen as a kid is learning a language. Because a lot is changing during those couple of years, right? Kids continuously learn a ton of new words, a ton of constructions. And so that landscape of language knowledge is very, very quickly evolving, and we're trying to see if we're able to capture those changes during that early development.
So this is a good segue to talking about what's next. So let's turn it over to Rebecca. Each of us will talk about what are some one or two examples of things that are on our roadmaps in our part of our missions in the Quest that are trying to move the cycle forward.
Yeah, it's so hard to choose because there's so many exciting things coming. But I thought I'd mention, because I told you about baby brains and the responses to faces, that's in a domain where we think babies start right away, right? Looking at other people and connecting to other people is the one survival relevant thing that a baby has to do at the day that it's born. And babies do within hours of birth. They look preferentially at faces and they recognize their own mother. So that was a case where we were studying something where the architecture had to be there right away. What I'm excited about in the coming 2 years, projects that are already well launched, is studying the neural basis of capacities that change dramatically in early infancy. So the two of those are navigation and language. In navigation, we again know a lot from Nancy Kemscher and others about the neural basis of the perception of scenes, the environment around us in adult brains. And in particular, a division of labor between the parahippocampal place area that tells me I'm in a seminar room, and the OPA, which tells me where the way out is. So we've been looking to study the origins of those representations in babies from an age where they can't move their bodies at all, they can't sit up or roll over, to an age where they begin to walk and have to make navigational choices for themselves. And I saw the first tiny bits of those data last night. So this is like just about to happen.
They do that by like seeing movies or something, right?
We show them movies of navigation from the first person perspective. And there's huge variability. Anybody who's had a baby, you know, there's huge variability in when babies start to navigate, right? My sons could walk before they were 9 months old, which was not a good thing because they would walk off of things. And other babies, you know, typically developing babies don't learn to walk until they're 14 months old. So there's massive variation in their experience of navigation that we can tap into to study how their visual systems and their intelligence develops. Similarly, in the case of language, this is the language system that Ev has so beautifully characterized for the last 20 years, and through our joint postdoc, Haley Olson, we're asking, what does the language system look like as you're first acquiring a native language? Scanning toddlers is the craziest, stupidest thing anyone has ever tried. Try to imagine asking a 1.5-year-old to lie still for an hour while they watch your stimuli. But it's incredibly important because there's massive variability in the acquisition of language. Healthy kids can range in their vocabulary size from 50 words to 5,000 words at the same age. And also some of that variability may predict important differences in school readiness and in cognitive development and in language skills for the rest of their lives. This is another thing where the complete data set may have just been collected maybe last week. I don't know the answers yet, but so these are, I think, big results that I hope to have within the next couple of years.
Speaking of toddlers.
So again, so many projects to choose from. I chose one that is a little outside distribution because I don't usually work on language. But I had the opportunity recently to look at word learning and revisit a project that we first had 10 years ago and failed. So there've been, gazillions of corpus studies of early word learning, parent checklists of vocabulary. So we know a lot about what children say, when they say it, even whole wired houses. So we see the input to children's words. But what nobody, I think for very sane reasons, has tried to ask is, given that children know, between 18 and 24 months, some 50 to 100 words, how do they decide what to say? By the time a child's a toddler, they have a life, right? They have bedtime routines and favorite toys and favorite stories and relationships with other people. And they, as we know a huge amount of the world before language, but they only have 50 to 100 words. So it's a huge information compression problem. What are they going to talk about and what are they going to say? Now we know as adults that if we have limited time and limited things to say, we are going to tend to talk about the things you do not already know. If I go to a coffee shop with you, and you step out to take a call, and a kangaroo walks into the coffee shop and then walks out the back door, and you come back in, I'm not going to say, oh, the coffee tastes great. I'm going to tell you about the kangaroo. So we thought that children might also be selectively informative in this way right from the start. So we tried that 10 years ago. We brought toddlers into the lab, and there were things the parent knew and the things the parent didn't know, and we wanted to know what the child would say. All of these are in the kids' vocabulary. And what we got was silence, because they're toddlers. There were just a handful of them. They're in a lab with a stranger. When they said things, they said mommy or up. Right? So there we go.
Which is the way
we now have now we have children helping science, right? And we were able in parents' homes to show toddlers these little movies where the parent and the child see a room with a bear in it. And then we say, now your parent can close their eyes and cover their ears. It doesn't really matter if they're peeking as long as the toddler thinks that they can't see or hear, right? And then the bear puts on shoes, right? And then the curtain closes, and we say, can you tell your parent what happened? Or the parent and the child see that there's a duck, right? And the parent closes their eyes, and a ball comes in. Again, what is the child going to say? Between 18 to 24 months, children know these words. They know bear and shoe and duck and ball. What are they going to choose to talk about? Now, if you're an engineer, that bar graph is not going to look very impressive to you. But let me tell you, those data points were hard won. We had 200 children, 6 trials each, so a potential 1,200 utterances, of which we got 90, right? And in those 90, we surprised ourselves. This is ongoing. But so far, children are systematically talking about what the parent does know. They are not mentioning the unknown thing. They're not being selectively informative. They're talking about what is in common ground. And this was really surprising to us, but any of you who maybe has tried to get by in a new language knows how much easier it is to talk about the things that are in common ground, the menu or the recipe, right, or the thing you want to order when you know. And if you try to talk about the vacation you took last year or the thing you're planning on doing next week that isn't in common ground, it's very hard to communicate. Communication can break down if you're a new language learner. So it may be very rational for early language learners to start out talking in ways where they can confirm that bear means what I think it does, and you know when I'm saying bear, right, what I'm talking about. Where if I say shaw, you might be like, what, right? You might think you're saying shoe, right? But it could easily vanish from the communication. This is important because we have computational models, actually, of rational speech act, and they are predicated on the assumption that speech is selectively informative, that efficient communication involves efficiently communicating information the listener does not know. And that may be true, but rational learning, rational communication, when it starts out, may look very different.
Okay, so you saw two examples of projects that are in progress developmentally, using new tools for studying brains and using new tools for studying infant and toddler and early child behavior on a big scale. And again, because of the tools and the community that Laura has built and the Quest has helped to build, and some of our early Quest funders, also Jeff Hallis over there, really contributed to this, in addition to CBMM and the Siegel family and some of our other great supporters. It's, the hard-won work of these couple of individuals is just part of this sea of researchers. You saw all those studies that are now on our platform. So my job as a computational modeler is to now take our model to the next step. So working with Rebecca and others, and Sherry Liu, who I mentioned before, we're trying to take that model of infant attention so it goes beyond just the very important first stage that built on Jim's work, which is like, when do you pay more attention or look longer or explore more at an interesting object, to these behavior scenes. When you see agents, even in surprising scenes, doing surprising things, what is interesting about this? When do you say, why is that person doing that? That's not what I expect. Where that person could be a little ball, right? But again, even young infants will get, we hypothesize, rationally surprised when they see agents doing things that they can't make sense of with their inverse planning model. So we're going to see if we can model that using the same kinds of ideas, but defined on these probabilistic programs now for our theory of mind. Or for example, again, you saw a little bit of this building on early things in what Jim showed before. Can we build these assistive systems by modeling how people understand what they want from an assistant in terms of both jointly reading our minds and communicating in language? So you may not be able to see in the upper right there, but a human, that's the little human-like robot. the black stick figure character has started in the bottom and taken a couple of steps up and to the left and says to the robot who's in the hallway on the other side, the robot who looks like a robot, says, can you hand me the red key? Can you pass me the red key? Notice there's 3 red keys, and this is exactly how we always communicate. We're totally ambiguous and underspecified. But if you look at the scene and you know that red keys of each color unlock those doors, you can say, okay, well, based on where the human is going, they must want to go to a red door, and the only one that would make sense is the red door on the left. Which is the red key that's closest and most efficient? Oh, it must be number 2. And that's exactly what people say, what our model says. Notably, those large language vision models don't do this. So this is one place where today's AI systems just fundamentally don't get each other's minds like this. But we think we can build models and then test them on a bigger scale in both adults and also see how these abilities grow as children start to cooperate in the earliest stages of language learning. So, yeah.
Cool. So to talk about maybe some of the future research projects on the computational side of things, coming back to the very beginning of this session, one of the things that I really want to emphasize is, in some ways, as little as we understand about, or as many questions as we still have about how human intelligence works, we have even more questions about what's going on inside these big models that exist today, right? We've seen many examples already today of sort of surprising failure modes and surprising successes made by sort of big deep network models. And we really, as a research community, have very little understanding of what's going on inside those models, very little ability to both describe what their internal computations look like, to predict how models are going to behave out of distribution. And so one thing that I think is going to be incredibly important going forward, and that I'm super excited to work on, in connection with the Quest, is building tools that actually help us improve our understanding of these deep network models, which, in some form are likely to continue to be an important part of whatever computational models of intelligence we build in this effort going forward. And so what I'm showing here is work by a couple of folks at MIT, including Sarah, who was a Quest postdoc at some point, on exactly this, on actually sort of artificial intelligence tools for running experiments and sort of producing large-scale characterizations of the internal computations inside AI models themselves. And I think, starting to have systems that can do this, that can describe sort of what features are getting represented, what internal computations are getting performed, is going to be a really useful tool for then figuring out what that next generation of systems ought to look like. And I think is something where just close connections with neuroscientists and cognitive scientists is going to be incredibly important. Computer scientists and sort of machine learning researchers as a field, I think, just don't have good languages for describing sort of the computations that underlie intelligence and for describing the kinds of circuits and mechanisms that we might expect to arise inside these models. And so having access to that language, having, sort of people who are used to doing these kinds of experiments on people, I think is going to be really important for understanding these automated systems as well. And continuing on that theme of sort of using AI tools to automate the construction and the understanding of AI models, another thing that I think is going to be incredibly important here is exactly that, is using sort of the systems that we have right now to help us design and to help us engineer the next generation of systems. We have seen at various points in today's presentation, I think we're going to see even more in Vikash's session in the afternoon, sort of explicit symbolic probabilistic models of reasoning, of computation, of planning that are able to give us much more robust and much more reliable and much more predictable and sample efficient computations for these kinds of cognitive tasks. And right now, the process of building one of these models for a new problem or for a new domain requires an enormous amount of effort, requires a sort of very clever grad student or a very clever team of grad students and postdocs and faculty to think very hard for, in many cases, years and years at a time in order to come up with the models, figure out how to do efficient inference in them, and run them. And if we want the ability to produce these sorts of explicit symbolic models, either so that we can put them into self-driving cars and be able to certify that those self-driving cars are going to do what we want to expect, or so that we can fit them to human experimental data, or so that we can use them as descriptive models of neural models, we're going to need tools to help us do this and to help us do it better and to help us do it faster. And so another sort of major effort that has involved a number of Quest members here. I'm highlighting Leo and Gabe, who are, I guess, current and former grad students here right now, is focusing specifically on sort of tools for automatically synthesizing models for cognitive modeling tasks. But I think this is actually a much, much bigger area and something with potential applications to many of the other kinds of things that Quest.
Can I give my less applied version of that?
Yes, please.
No, well, I mean, this has been one of my biggest long-term collaborations with Jacob. These are joint students that we both advised, and one way to think of this is, we're trying to understand how natural language can be used as a tool to synthesize code in these probabilistic symbolic world models. Or the way I think of it as a cognitive scientist is a model of how people understand language and how people use language to communicate thoughts, like just what we're doing now. So just as you heard from the beginning, just how do we scale the models inside our own heads? So much is not just from our own experience, it's from people telling us things. So whether it's a model of how we build our models from people telling us things, or how we can get machines to better scale models by us telling them things, then this is one of the most exciting projects that we're engaged in. Okay. And that's a good note to turn over to F. Yeah.
Just very briefly, one big question that still remains is what is the structure of thought? What is the ontology of reasoning, right? I've put all these different pieces there, but it's not like each of them draws on a separate system in the brain. But it's also not the case that thought is just this nebulous, unstructured set of computations. So there's been a few systems that were quite carefully characterized over the years. So one system that highlighted in green was a system that Rebecca discovered discovered and characterized, a system that supports social reasoning. All of the blue things, the dark blue things, correspond to a system that supports formal reasoning, formal abstract reasoning, and things like mathematics and logic and computer programming all load on that system. And all of these are distinct from language again, right? This is just now thinking about the structure of thought. And then there is a system for episodic memory, remembering the past and imagining the future, the ping. But then, just in the last few years, a few other systems were discovered, and this kind of gave me pause, because I thought we kind of figured out the rough cuts in that space, suggesting that there's many other pieces that we may not know yet about. So for example, work in Nancy's lab, joined with Josh, has been characterizing the system for reasoning about the physical world. Also work in Nancy's lab is finding a region that seems to be specific for causal reasoning, which is, of course, obviously a very, very important piece of reasoning that we rely on starting early in childhood. And then Hope Keen in my group is discovering what seems to be a region specific for logical deductive reasoning, which is obviously something that is likely, well, is likely human specific, so ontologically probably developing quite late. But this is all to say that there's a lot of pieces that we just don't even know how they are implemented, whether they are fully distinct or partially overlapping, drawing on the same representations. And a big open question is how to build models that implement these different pieces of cognitive machinery that humans have, and on our side, on the cognitive side, understanding how they all develop. And then I guess a big part connecting it back to language is understanding how does language interface with all these systems. Because as I said, language is so deeply embedded in everything we do in everyday life. Trying to understand that interface, how do we continually translate between these abstract structured representations supporting thought and noisy kind of linguistic, imprecise, vague descriptions, right? We do that all the time, back and forth quite effortlessly. And across a bunch of different domains, we're trying to understand how might that happen.
And here we're talking about basically like the neurosymbolic models are the models that you just saw from Jacob that we've been building. And we think these could be the models of how the language network in the brain and these other networks, potentially, this one candidate hypothesis, how they might interact and interface and grow thought. Okay, so we just have a couple of minutes, and we'll just turn to our last item. Feel free to just talk if you want, or I have your slide contributions if you want. But where do we see the impact in the real world from this kind of work? I don't know. I think Ev, maybe if you want to, or maybe Jacob first. A few of us are very interested in education, so I don't know.
Yeah, I mean, the first piece of this is that, and coming back actually to several of the slides that we saw before about sort of theory of mind and inverse planning, these things are especially important once we start to think about, systems that are not just good at making predictions about humans, but that are actually interacting with people, especially in pedagogical settings. And so my student Alexis Ross lately has been thinking a lot about sort of AI tutors and ways of sort of offering personalized education to individual learners in settings where that's not otherwise available. And it seems to be the case that the real bottleneck there right now with sort of all of the pure LLM-based systems that we've been trying to build is that they're actually quite bad at drawing inferences about what it is that individual learners know or don't know and modeling sort of the progress of their knowledge over the course of a tutoring interaction. And so a lot of what we're thinking in this direction that I think can build on a lot of the sort of explicit computational modeling of theory of mind that other folks are doing here is using these as actually mechanisms for building tutors that personalize their tutoring strategies to individual learners and really understand what people know.
All right, Ev, I didn't have a slide from you, but do you want to say about any of the educational things you're thinking?
Yeah, I just want to add that these models are also a really exciting tool to understand how things break and how to fix them, right? Because humans break in very messy ways. Like when a stroke happens, it doesn't follow precisely a particular pattern of functional divisions in the brain. But using these models, once we build a system that we understand well enough what the pieces are and how they go together, we can precisely simulate different kinds of impairments by lesioning different components of the models using the kinds of approaches that have been long used in animal literature, which we just can't do with humans. But with models, we have that ability to impinge on, to interfere with models in all sorts of controlled ways to try to understand what exactly leads to problems. And once we understand what pieces are critical, we can try to understand how to potentially fix them, to bring them back online, or to leverage existing remaining pieces to lead to the same kind of performance.
Yeah, like how our brains get it set up, education, and how to keep them from breaking. On the but I mean, those are two key impacts. And like, people often talk about in many areas of like education and mental health, they say, well, imagine if it was like cardiology, where we actually had a theory and a model of how the heart works as a pump and understand fluid mechanics and other things. And imagine if we had that for the mind and brain. Well, it is worth actually trying to deliver on that. And on the education side, another direction of yours that I'm really excited about, and I think it's something that's a good joint project, is like math gets hard when people try to teach kids word problems, because sometimes you get tangled up. Is it about the words and the language, or is it about the math or the algebra? And yeah, some of our Quest teams, like Ben Lipkin and others, are working on how to understand that better, which we think can lead to much better, not just everything better when in the parts of STEM education that are most challenging for kids. One more thing about education, and then something back about mental health.
So what I was going to talk about is I think not especially glamorous, but it's eminently practical at the moment, and something we're actually about to try to do. I mentioned earlier the enormous difficulty of doing longitudinal testing and pre and post testing, and how very difficult it has been actually to look at the effective interventions. And one of the peculiarities right now is about 70% of preschoolers are running around with these pretty high production value, very affordable, very scalable educational apps, and we don't know which, if any, of them work or have an impact on children's learning, except for some small-scale studies, and even those get lost in academic papers. So we have this tool right now, Children Helping Science, which I think we can turn into Science Helping Children, where there's no reason not to conduct rapid cycle, reproducible, open access, randomized controlled trials on which of these work. Because some years ago, Atul Gawande came out with an article in the New Yorker where he pointed out that if we did better care of high blood pressure and diabetes management, we would have a bigger impact on public health than any new drug or discovery ever could make. It's incrementalism that would lead to the biggest innovations. And I think it's likewise true here that if any of these work, they are unlike, I don't think any of them are going to have the impact of a caring teacher or parent, those relationship-based, deep, connection-based learning. But those are not affordable and scalable interventions. These are, and they're in families' hands. So if any of them were effective, those easily adopted interventions could actually make a big nationwide or international impact on things like kindergarten readiness. So this is a project we're actually just going to start. And to be clear, this is not about AI. We can do this with the tools we have right now. But if we are going to use AI to build new educational interventions, we need these kinds of benchmarks. We need this infrastructure and community present to be able to test their efficacy to know what works. So we can start here, and I hope next time I get to talk to you, I can tell you not only what works today, but why we think the future of educational interventions may be even more promising.
And every one of these apps, and every game really, in a sense, is a new lab, right? A new lab for studying cognition. And that's I think that's like, people like math apps, and they're fun because they're games in some form. So this idea that the tools that we're building can turn, in a sense, like any game becomes a way to study how the mind works. Any tool for teaching is both a way to show that our theories of learning are actually doing work, and a way to help keep growing and testing those theories. So we really are excited about what that potential can look like going forward for an understanding of how our minds work and learn, to actually, make us have AI that can actually make us smarter. So that's a good note to end on, I think, and really appreciate your joining us for this session. Next up is going to be lunch and some really awesome demos. You'll get to see some of these things being demoed by the people who've built them, as well as some of the demos of the embodied intelligence, robots, perception, things that you're going to see later in the afternoon. So that's probably actually the best part of the day, will be the demos from our students, postdocs, and research staff. So make sure you make the rounds and see them. Okay, thanks to my fellow speakers, and thanks for your attention.